All right then, good morning and welcome to Remote Learning 9, where I'm going to continue working with the differential equation questions from various AP exams of the last couple of years. This seems to be a popular style of question in the free response, and I just keep finding them, so I'm thinking that this is a good way to spend our time, especially for those who are taking the AP test, but of course, even for those who are not. These are super solid questions that are making us really think about derivatives and integrals and the applications of those. So, okay, so on this current problem that's here, I believe this was 2000 and I have it written down. So this is the 2016 exam. Free response question number 4 is to be done without a calculator. So keep in mind that you will have calculators at the ready, so these can be made more easily done with a calculator, but then again they're quite theoretical, so they don't really save you so much time. Okay, so here we go. So number 4, consider the differential equation that is given by dy dx equals y squared over x minus 1. So notice that it is in 2 variables, but most importantly, remember what dy dx is. It is the slope of the tangent line that butts up next to some curve that we do not have the equation of. And the way in which this calculates the slope of that tangent line is it requires that you know a coordinate on the function. So you put its x and y value in, and then this gives you the slope. Okay, so on the axis provided, sketch a slope field. So in the previous problem, we saw that they gave us a slope field. We were to draw the equation going through the slope field starting at some given point. And that's really like a tracing exercise where you follow the slope until you run into another slope, and then it changes slope, and then you follow that slope, and so on. So this is the reverse of that. This is to sketch a slope field for the given differential equation at the 6 points indicated. So like a slope field has infinitely many points, well, we can't really draw a slope field, but we can draw some components of a slope field. So they gave us the exact points to draw the slopes of. Okay, so I can pull that then into my discussion up above of what dy dx is, and go here to 0, 0, and essentially I am going to be calculating dy dx at 0, 0. And that gives me 0 over negative 1, which is 0. So that part of the slope field is done by that. Okay, so then I just keep on doing that. And I'll write these down and move quickly. So let's see, the next one, I'm going up. That would be 0, 1. Just be careful where you're putting things. I'm putting 0 in the x spot, and I'm putting 1 up there in the y spot, and that gives me negative 1. So there's that slope. Okay, so you can see this is an easy question once you understand what they want you to do, and it's just a matter of knuckling down and doing it. Putting 0 in again for x, and putting 2 in for y for negative 4. So that's more difficult to draw, but it's steep and negative. Okay, so then let's squeeze in one more over here. I've got dy dx at, what is that? That is 2, 0. So let's be careful because we fall into a pattern there. Putting in 2 for x, I get 1. Putting in 0. Okay, so that's 0 again. So I got another flat. And at 2, 1, let's see, so 2 comma 1. And what do I get? 2 for x puts a 1 down bottom, and that's a 1 on top for a slope of 1. My guess is this is going to be positive 4, but let's just see it happen. So dy dx over here at this last one is 2, 2. All right, so we know that's a 1. Oh, yeah, there it is, 4. Okay, so then that steepness is positive 4. All right, so then that is the answer to part A. They just want you to make little marks as if you're drawing a slope field for the points that are given. B. So let y equal f of x be the particular solution to the given differential equation with the initial condition f at 2 equals 3. So as I mentioned, this is not the actual function. This is just its derivative, right? So then we're looking for the actual function, but in order to do that, then oh, that's actually not what we're doing. Okay, it's just setting up that that's what it is. I think that's going to be part C to go find it with the initial condition here. But okay, so given that there exists some function y equals f at x with an initial condition f at 2 equals 3, so input 2 and output 3, write the equation of the tangent line. Okay, so that's what we're after. Write an equation for the line tangent to the graph of such an equation at x equals 2. Okay, so, and then we'll use it to approximate something. So we've seen this, and so let's go for it. In order to find the equation of the line, I'm going to go first, hunt out the tangent line slope, and hey, lucky for us, we have the exact tool that we need. We're going to find the slope. Now we do need an x and a y value, but the point that we're at was given. We are at 0.23. That is the point that's on our curve, y equals f at x, but it's also on our line. And that is the point of tangency. We want to know the slope there. So we've got everything we need in order to do that. And let's see. So I put 2 in for the x value. That's 2 minus 1 for 1. Put 3. And okay, so then the slope is 9. Okay, so if I can turn this into a coordinate and use point slope formula, and Gianluca, now I'm a big fan of point slope. I used to not be such a big fan of point slope, but it does make this sort of work really easy. Okay, so what do we've got? We've got y minus the y component equals the slope times x minus the x component of our point of tangency. And I made quick work of that, but that is the equation of the line tangent to the graph of our function at 2, 3. All right, so we could rearrange this if they asked it in y equals mx plus b form or whatever, but that's the equation for our line. I'm done. All right, so now moving on to part C here. So let's see, find the particular solution y equals f at x to the given differential equation when the initial condition is the same one as before, f at 2 equals 3. So now they actually want us to go find f at x. Okay, so we do this as we have done. This is, the process known as separation of variables. So let's get the original differential equation up on this part of the screen, because I know I'm going to require some room here, and do the separation of variables. So let's see, I want all the y stuff over here on the left. That's going to require dividing by y squared on each side. And I want all the x stuff over on this side, so that's going to require multiplying each side by dx. Okay, so I've got it looking like a run-of-the-mill differential equation after we've done the separation of variables, and then now it's time to integrate throughout. Okay, so over here, that's essentially y to the negative 2. So on the reverse power rule, we get negative y to the negative 1. And then over here, you can do a quick little u sub, or this is just that pattern that is so prevalent. That is the natural log of the absolute value of x minus 1 divided by its derivative, which happens to be 1, and then plus some constant that I'm now going to go and find. because I have some initial condition. I know that when x is 2, y is 3, so then I can go find this constant. Okay, so I'm going to do this up here. So I'm just going to write at 2, 3, and we have this. So what do we have? We have negative 1/3 equals the natural log of 2 minus 1, which is 1, plus c. And the natural log of 1 is the question e to what power makes 1. Of course, that's 0. Okay, so then I've got my solution. It's I'm going to bring it over here because it's going to require some work to solve for y. So I've got negative y to the negative 1 equals the natural log of the absolute value of x minus 1 minus 1/3. And then the annoying process is the algebra required to solve for y. Okay, so I'm going to do that. And let's see. I see this as a fraction. So that's going to need to be flipped. And in order to flip it, it's going to be convenient to have this as one single fraction. So I'm now embedding a couple of steps here. But I'm making a common denominator of 3. So I multiply the top by 3 and the bottom by 3, and I have a common denominator. Okay, so then that allows me to flip this one and then flip this one. You can't flip with a minus sign or a plus sign there. So I had to write this as a single fraction. That's why I did that. So 3 natural log of the absolute value of x minus 1 minus 1 on bottom. Okay, and then lastly, we could write this as they wish and throw the negative sign up on top. Okay, so there we go. I made quick work in number 4. Now that we're warming up to these differential equation properties, and I can see some alternative version of this now that I'm just staring at it for a second. Multiply the top by negative, multiply the bottom by negative, which is essentially commuting around that, and I can make it look a little better. They are not going to care if these are both totally suitable answers, but if your brain went here, or if you paused it and tried to do this by yourself and you got that answer, then there you go. Okay, so in thinking through this problem and whether or not, it was in the calculator or no calculator part of the exam, and then realizing that you will have access to a calculator, just a suitable question is, well, would the calculator have helped? And I really don't think that it would have sped anything up with these simple computations in part A and B, and there's not really any super big computations in part C either. But I am going to take a moment to show you that because we have a calculator, we can make some strategic moves, and the strategic move to do on this problem is to avoid having to do any of this work. So that's a pretty complicated, equation to solve here. I mean, it wasn't that complicated, but it also took a fair amount of time, and you could make some mistakes. So it would be nice if they threw something like this at you, and it wasn't a requirement that you show your steps or something. We could then use the calculator to do the solving for us. So I want to show you that. And additionally, I know that Dylan and Mateo in particular have approached me about showing calculator tricks and such. So yeah, here comes a pretty awesome calculator trick, and that is to solve this equation without doing any of those moves. All right, so here we go. CAS mode and toolbox, solve. type it in. Okay, so we've got negative. We've got a y hidden down here. It is hidden. There it is. So it's y to the negative 1 power. And then that equals, so equal sign, and what equals to the natural log of x minus 1. I know it's absolute value, but I can use x minus 1 in parentheses. It's not going to change the algebra. And then that is, oh yeah, I shouldn't be looking over here. I should be looking over there. It's minus 1/3. We do have a constant. Okay, so making sure that I type that right, that's negative y to the negative 1 equals the natural log of the quantity x minus 1 minus 1/3. But who am I solving for? Well, we have to tell the calculator that. I know I'm solving for y, but I have to tell the calculator that. So it's comma, the variable that you want to have isolated, snap-a-rama, and that's pretty awesome. Okay, it just solved it right there. There it is. 3 divided by negative 3 natural log of x minus 1 plus 1. Ta-da! Okay, so brilliant stuff on the calculator if you know how to use it as a time saver. And yeah, I didn't make any mistakes. Okay. Moving on. Okay, so let's see. I've got 15 minutes to do one more before I let you loose on one of your own. And here we go. This is consider the differential equation dy dx, which equals this two variable function, 2x minus y. I don't need to reiterate what we have there. We do not have the original function. We have its derivative. On the axis provided, sketch a slope field for the given differential equations at the 6 points indicated. Okay, so that is super tedious now that we know how to do it. So let's see, can we move through this more quickly? I can do it in a really weird fashion. Bam! Let's go with this point down here. So that is 0, -1, right? Think through. You don't want to be putting your numbers in the wrong spot. That leads to +1. Okay, then we're going to put in 0, 1, and that's going to be -1, so that one's looking like that. And then the one above that is 0, 2, and when I do that, that's -2, so that's steeper but still downhill. Okay, and then what do we've got? We've got 1, -1. And 1, -1 is going to be, let's just slow down here so I don't make a silly mistake. That'd be 2 + 1 for 3. So this one's looking more steep. And then we've got 1, 1. And then that's 2 - 1 for +1. So then there we go there. And let's go with 1, 2 is the last one here. And when you put in 1 for x and 2 for y, you get 0. Okay, so same sort of deal. There we go. I made quick work of that. Moving on. Find the second derivative in terms of x and y. So that, that's a pretty big hint there. And let's see, determine the concavity of all solution curves for the given differential equation in quadrant 2. Give a reason for your answer. Okay, so quadrant 1, quadrant 2, we don't have anything over here. Okay, and so this is going to be a little tricky, but maybe let's just not even think about that quite yet until we find the second derivative. And then maybe when we look at the second derivative and reread it, then maybe we'll have some insight. Okay, so finding the second derivative of this differential equation. That's the command to take the derivative. We're supposed to take the derivative of the derivative dy dx. So I can set this up looking like this, where I take the derivative of each side. Okay, so over here on the left side is then the second derivative. So I'll just move that into its notation. And the reason that this notation is the way it is that you can see that you have a d dy, so that's the d squared y approach. And then on bottom you have a dx dx, so it would be better notation if it was written like that. And my guess is once upon a time it was, but then, okay, it's a concept, so you don't really need to have like perfect notation. But okay, so that's the second derivative. And in order to find the second derivative, I then need to differentiate each of these terms. But then you need to be careful. You need to remember that y is a function of x. I mean, my guess is part C is going to be, hey, find the function y equals f of x, right? That's the deal. So we need to remember that we have essentially a variable mismatch here, but we can think about y as some x-like stuff. We don't exactly know what it is. Okay, so then let's continue on here. I've got that the second derivative is equal to, well, this one's easy, that's 2, and then I need to subtract from that. And, well, we can't take a derivative of something that we don't know what it is, but we can write that symbolically. And as soon as you write that symbolically, you may realize, hopefully you realize, that dy dx was given. Dy dx is up here above. Dy dx is this thing right there, 2x minus y. Okay, so moving this over then, I've got the second derivative is equal to 2 minus 2x plus y on the distributing of the negative sign. Okay, so now let's move on to this part about concavity. It says to determine the concavity of all solution curves for the given differential equation when we're in quadrant number 2. Give a reason for your answer. All right, so concavity. Concavity is based upon the second derivative. So I'll remind you over here, and we can just maybe rethink about it. When the second derivative is greater than 0, okay, so then we have a scenario when the second derivative is greater than 0 that the tangent slopes are increasing. The first derivative is increasing. The first derivative is the tangent slopes. So that's something like from negative to positive. So that's when you're on concave up. Okay, so concave up. See, most people would think, oh, hey, let's memorize all these like little rules. I don't know. That's just not how I work. I think them through. Now I know this is going to be concave down, but just think it through with me. That when the second derivative is negative, then that means that your first derivative is decreasing. So it's going from a positive slope to a negative slope as you move from left to right. And then, of course, that's concave down. So concave down. I guess I can write it. All right. So we're interested in whether or not this value is positive, and then we'll know we're concave up, or negative. But we're not interested in one particular point. We're interested in things like everything that's over there in quadrant number 2. So I would remind you, in quadrant number 2, x is negative, because you go left, and y is positive, because you go up. You go left and up to get into quadrant 2. And when that's the case, so therefore, therefore the second derivative is greater than 0. And it's greater than 0 because this is a positive thing, that's 2. When x is negative, you have a double negative, so that's a positive thing. And y is a positive thing, so you're having all positives. Okay, so then the answer is concave up. Okay, so then reread it and make sure you've answered everything. Find the second derivative in terms of x and y. Check, check, it's right there. Determine the concavity of all the solutions in quadrant number 2. They're all concave up. Okay, so I got that one. And give reason for your answer. This is my rationale. And I think all of the work shown here is sufficient. Okay, so then let me just do a quick time check. And I can do it in 3.5 minutes or 4.5 minutes, whatever I have here. I'm trying to stick to the half hour. Ooh, maybe I can't do it with part D there. That's going to be tough. Okay, so let's see. Let y equal f of x be a particular solution to the differential equation with the initial condition f of 2 equals 3. Does f have a relative minimum or relative maximum, or neither? Justify your answer. Okay. Does f have a relative minimum? So that's what? A valley point. A relative maximum, a peak, or neither? Well, I know that those relative extrema happen at critical points, and critical points happen when the first derivative is 0, right? Where the tangent slope is flat, you have these critical points. So let me investigate whether or not we have a critical point. And by finding, I'm given this initial condition over there, so I can use my first derivative, my slope calculator, and I can drop in 2 for x and 3 for y, and see that I get 1, which is not equal to 0, therefore no critical point. So neither. And part D. Find the values of the constants m and b for which y equals mx plus b is a solution to the differential equation. All right. This one's tricky. It doesn't follow suit with the other ones, where late in the problem they ask you to go find the function f of x, and they give you some initial condition, and we do separation of variables and so forth. Okay, so this one is definitely tricky because it doesn't give you an initial condition, and the question is to find these m and b values for which the linear function y equals mx plus b is a general solution, is a solution to the differential equation. This one's going to meander around a little bit, and then there's definitely going to be an algebra trick. So let me roll into this. If y equals mx plus b is one of our solutions to the differential equation, if it's a general solution to the differential equation, okay, then what we know about y equals mx plus b, which is given in the early part of the problem, is that its derivative is this 2x minus y. All right, so I can also point out that over here, if we differentiate each side of this linear general solution, we simply get m. So you can make the observation then that dy dx equals m, while dy dx also equals 2x minus y, where y is the general solution to our differential equation. So they are saying that our general solution is in this form mx plus b, so I'm going to go one step further and swap out y with mx plus b. And then it's this equation that is going to ultimately lead me to m and b, because I now have an m and a b. But okay, so this is a really tricky equation to go solve for m and b with the 3 variables running around the problem. And there's going to be an algebra trick that I'm going to use in order to do that. Okay, so let's see. I'm going to distribute the negative. And all right, here comes the trick. It is a trick that is very similar to what happens when you work with partial fractions. So when we do partial fractions, at some point in the process, we compare terms by their orders and then build a system. So there's an x squared coefficient on one side of the equation, and there's an x squared coefficient on the other side of the equation, and you compare them, and that becomes one equation. And then there's an x coefficient on one side of the equation and a different x coefficient on the other side, and then that becomes equation number 2, and then you compare the constants for equation number 3. Okay, so that's the general idea. And so what we're going to do is we're going to compare like the x information with the non-x information. But in order to make that a little more obvious, I'm going to do this. Okay, so I'm going to minus b from each side so that I have 0 equals 2x minus mx minus b minus m. And I'm going to write this in a crazy way where that's 0x plus 0, setting up this comparison idea. And over here, I'm going to factor out an x. And I guess I'm just going to leave this all alone, although I could factor out a -1 or something. But okay, so then when I look at this, I can make the observation that there's two things going on. 2 minus m must be 0, and negative b minus m must be 0. And this is just like a really cool way of solving for m and b. I now know that m is 2 over here, and if m is 2, then b is -2. And that answers the question. Find the values of the constants m and b for which y equals mx plus b is the solution to the differential equation. Okay, so recapping, and I think I'm over on my time a little bit, but it's not too bad. Okay, so recapping, it is, if this is the solution, then its derivative must be 2x minus y. So dy dx is 2x minus y. Okay, but the derivative of y equals mx plus b is m. So then m is equal to that one. But it meanders around a little bit when we realize that y is some function of x, and we exactly know its structure, mx plus b. So then we swap it out again, and the rest of it is that grouping strategy of solving for 2 variables in a 3-variable equation. Okay, and the homework. So there's one problem that I want you to do, and here it is. So assignment part 1 is in front of you, and I will see you in the Google Meets. Please don't forget there's the live board and the Google Open Meet, and you can certainly email me questions or show up in the meets. I'll be there for you as needed. Okay, thanks everybody.